Hello, my name is Ima Frank. We are still in our series of study in functions of several variables. And so in this package, we are going to look at the Jacobian of functions of several variables. Now, let's define the Jacobian of functions of several variables. Let u of xy and v of xy be functions of two variables x and y. The Jacobian of u and v denoted by or the Jacobian is denoted by this symbol, or you can write it this way. Is defined as Jacobian of uv with respect to x and y is equal to the determinant of the first derivative of u with respect to x, and then first derivative of u with respect to y, first derivative of v with respect to x, first derivative of v with respect to y. That is, we have partial u partial x, partial u partial y, partial v partial x, partial v partial y. That is the Jacobian. So, similarly, if we have a function of this form, u of x, y, and z, then we also have v of x, y, and z, and we have w of x, y, and z. Notice that these are three functions that are depending on x, y, and z. Three functions. So if we have these three functions, the Jacobian of u, v, and w denoted by u, v, w with respect to x, y, z, or we write it in this way: u, v, w, and then x, y, z is defined as the product of u, v, w with respect to x, y, z will be equal to the first derivative of u with respect to each independent variable, the first derivative of v with respect to each independent variable, and then the first derivative of w with respect to each independent variable, and that will give us partial u, partial x, partial u, partial y, partial u, partial z. Then we also have partial v, partial x, partial v, partial y, partial v, partial z, partial w, partial x, partial w, partial y, partial w, partial z. So the Jacobian is equal to the determinant, the third order determinant, and that is for three functions. Then if you do it for two functions, you also have the second order determinant or first derivative of the function with respect to each independent variable. So that is the Jacobian. Now we are going to look at the example how we can solve problems relating to Jacobian of functions. If x is equal r cos theta, y is equal r sin theta, find the Jacobian. Okay. Find the Jacobian of xy with respect to r theta and the Jacobian of r theta with respect to xy. Now we are going to take this example based on what we have to find the Jacobian of functions to be, and here we see that we have two functions x, y. Now x is dependent variable because x depends on r and theta, so it's y depending on r and theta. Okay, so we take the solution in this way. We have x is equal r cos theta, partial x, partial r, of course it will be cos theta, and then partial y, partial r will be equal sin theta. Now we also go for partial x, partial theta. So if we go for partial x, partial theta, we have minus r sin theta. Then partial y, partial theta will give us r cos theta. So we now define the Jacobian. Now find the Jacobian of xy with respect to r theta. And we know that this will be the same as x y over r theta will be equal to partial x, partial r, partial x, partial theta, then partial y, partial r, partial y, partial theta. And if we have that, it will be equal to putting the values, the respective values in the determinant and taking the determinant of this second order. Now this one, we can write it, which is this partial x partial r is cos theta. Then partial x partial theta is minus r sin theta. Partial y partial r is sin theta. Then partial y partial theta is r cos theta. So we have it. Now which is the same as, taking this determinant, we have r cos square theta plus, because it's invisible minus, plus r sin square theta, which is equal by factor out r, which is sine square theta. Now we know that cos square theta plus sine square theta is 1. So we have that this is equal r times 1, which is r. So that is the Jacobian of xy with respect to r theta. Now we want to look at another one, which is the Jacobian of r theta with respect to xy. That is what we want to look at now. Now we know that x is equal r cos theta, and then y is equal r sin theta. Then what we need is the Jacobian of r and theta with respect to x, y. And then we see the equation is not expressed in the form where r is a function of x and y, or theta is a function of x and y. So we are going to make r to be a function of x, the r, yes, to be a function of x, y, and then theta to also be a function of x, y. And so to do that, we go to the plane. You know, in the plane, this is the origin. We have a vector that is going this way of magnitude r, and then it makes an angle theta with the positive x-axis. Now, this is y-axis, which we know, and this is the x-axis. Now, this axis of y is here too, so I can write y, which corresponds to the point where this vector terminates, at the point where it terminates. So in this way we also have x. Now what happens is that we know that by Pythagoras theorem, we know that r square is equal x square plus y square. We know that r square is equal, that is r square, the hypothesis is equal to the sum of the square of these two sides, which we know from our elementary trigonometry. So if we have that, we can also express theta. And look at this, theta. You know, tan theta is equal tan opposite all over adjacent is equal y all over x. So that implies that theta will be equal tan inverse of y all over x. Yes, so that is theta. Now here we see that r is a function of x and y. That means r itself is the square root of x squared plus y squared. Okay, with this we can then find partial r, partial x, and partial r, partial y. How? By differentiation, by implicit differentiation. We know that we can differentiate if we know that r squared is equal to x squared plus y squared. Could be represented in this way. 2r, you know, if you differentiate this, you have 2r. Partial r, partial x will be equal to x. I'm differentiating with respect to x, so not with respect to y. So that partial r, partial x will be equal to x over 2r, which is equal x over r. And this is the same as cos theta. How? Because in the plane, if I need cos theta is adjacent all over hypotenuse, which is x over r. So that's why I put cos theta there. Alright. So that means partial r partial x is cos theta. Now let's go back here and also find partial r partial y, and that will give us what? 2r partial r partial y will be equal to y if I'm differentiating with respect to y, so not x this time. And so I have that partial r partial y is equal to y over 2r. This cancels this, so I have y over r. Now, what is y over r? From here, you see that sine theta is opposite all over hypotenuse. So I can say that this is the same as sine theta. Alright, so what I need again now is theta, because I need a partial theta partial x, partial theta partial y, so that I can form my Jacobian. And so what I will do now, from here, I can differentiate from here. And so we have that theta is equal tan inverse of y over x. So partial theta partial x, I'm differentiating theta with respect to x, will give me 1 all over 1 plus y over x squared. You know, it is assumed that you are very familiar with elementary calculus. In elementary calculus, if you differentiate, maybe you have y is equal tan inverse of x. If you watch our lectures on elementary calculus, I'm showing the proof. And so if you have this, you have that dy all over the x will be equal 1 all over 1 plus x squared. That is what it will be. So now that I'm differentiating theta, I have theta is equal tan inverse of y over x. Now look at this place. Look at this place as x, or any variable, maybe u, but here u. So what I have is theta is equal tan inverse of u. And so when I differentiate, when I say partial theta partial u, then it will give me 1 all over 1 plus u squared. And that is why this is my u. When I say calculus. And so this will give me the same as 1 all over 1 plus y squared over x squared. Times, now is it, this one needs understanding of functions of several variables. Even when I differentiate, even when u is this, so it means that u is equal y all over x. It's a function. It's a function of u itself. It's a function of y and x. So if we differentiate this by quotient rule, u will now give you minus y over x squared. That is what you will give you. Okay. I think let's do the practical part of this so that we'll also get it right. Now u is equal y all over x. Look at this is u. So by quotient rule, I know that this one, let me use g, so that now let this be u and let this be v. By quotient rule, I know that the g all over, partial g here, because of what we have here now, will give me what? The g all over x. If I'm differentiating with respect to x, it will give me what? I'll first keep v, and v here is x. Okay, I'll first keep v, and v is x, times the differentiation of u, and there is no x in this place, so it becomes 0, minus, I'll keep u, my u is v, times the differentiation of x, which is 1 over x squared, that is v squared. And so what I have here is minus y over x squared. Look at that. When I differentiate u itself, then when I differentiate theta with respect to u, I will have 1 over 1 plus u squared. Now, this is how we differentiate functions of several variables that involves this. Now, if you look at that, you now see that if I take LCM of this, I'm going to take LCM of this one, then I will have 1 over x squared plus y squared over x squared. You know, my LCM is x squared. So this is over 1. X squared divided by x squared times here, you have x squared. Then if you go this way, you have y squared over x squared times minus y over x squared. Okay. Now if you do that, you now see that this one can cancel this. Of course, you know that this minus y here, let me take it off so that you see it. Minus y is here over x squared. Now the side is right because it's this up one. And then this can cancel this. So what we have there become that partial theta partial x is equal minus y over x squared plus y squared, which is equal minus y over r squared. You know why I said r squared? Because originally we define r. Look at what we define r. Define r squared to be l squared plus y squared. So because I have l squared plus y squared, I can say that it is equal r squared. And if that happens, I will now have I can now have something of this kind. I have minus 1 all over r times y all over r. You see, I try to simplify it. Because if I time this and this, to give me r squared. So, but I know the definition of y over r. Yes, from here. Y over r is sine. So what I have here is minus 1 over r sine theta. That is partial theta partial x. Then we can also find partial theta partial y. Now, we know that theta equals tan inverse of y over x. Okay, now let me show the full working this one so that now let u is equal. Okay, let me use u. Let u is equal y all over x. Let u is equal this place. So this implies that theta is tan inverse of u. And then partial theta partial u is the same as 1 all over 1 plus u squared. Okay, now partial u partial y, because what I think is y, partial u, yes, partial y, and differentiating this with respect to y will be what? I will have x times, I will keep v first. Then if I differentiate this, I have 1 minus y times 0 over x squared. Now this will give me, this will be 0. This times 0 has gone. So I have x here. I have x over x squared, which is 1 over x. So this cancels this. So that is partial u, partial y. But what I need is partial theta, partial y. And I know that partial theta, partial y will be equal partial theta, partial u times partial u, partial y. Yeah, because this time is chain rule for probability calculus. You see, everything started probability calculus. Yes. Now, if I substitute this, I will have that partial theta partial y is the same as partial theta partial u. Now partial theta partial u is 1 all over 1 plus u squared, and then we know what the u is. Look at that is y over x squared times partial u partial y, which is 1 all over x. Now the same procedure can apply. We have 1 all over 1 plus y squared over x squared times 1 all over x. If I take LCM here, I will have x squared plus y squared. That is for here. But we have 1 all over x squared plus y squared over x squared times 1 all over x times 1 over x. Now this is the same. This can cancel 1 here. Right, so what I have here is 1 over x squared plus y squared over x. Now, if I have this, it is the same as writing x over x squared plus y squared, which is the same as x all over r squared. We know that r squared is x squared plus y squared. Now, this is the same as 1 over r times x over r. Yes, because this time this is this. Now, it means that partial theta partial y will be the same as 1 all over r times, we know this to be, that is, we know x over r to be what? Cos theta. So now we are able to get partial r partial x. We are also able to get partial r partial y. We are able to get partial theta partial x, and then we are also able to get partial theta partial y. So we can now take the Jacobian. Recall that the Jacobian we are looking for is the Jacobian of r theta all over what? X and y, and it will be defined as partial r partial x partial r partial y partial theta partial x partial theta partial y, the determinants of this. And so we are going to fix those values now, and then it will be equal partial r partial x. We have partial r partial x to be cos theta, then partial r partial y was sin theta. So I just put that cos theta sin theta. Then we also have partial theta partial x. Partial theta partial x was minus 1 over r sin theta. So we have here minus 1 over r sin theta. Then partial theta partial y is 1 over r cos theta. Okay, so we are able now to express the Jacobian of r and theta with respect to x and y. It's very simple. It's very simple that way. Just understand the coordinate plane, and then you can know your r and know your theta from there. It's very simple to deal with. Now, we want to take the determinant. So this time this gives us 1 all over r cos square theta. Now if you go this way, there is invisible minus that exists. So you have plus 1 over r sin square theta. And next, if we factor out 1 over r, we have 1 over r cos theta plus cos square theta plus sin square theta. Of course, we know that this is 1 over r times 1, which is 1 over r. So that is the Jacobian of r and theta with respect to x and y. Yes, it's very interesting. Now, we are looking at another example. If u is equal to x, y, z, v is equal to xy plus zx, w is equal to x plus y plus z, compute the Jacobian of u, v, w with respect to x, y, and z. So, in this one, we see that we have three functions of three independent variables, x, y, z. So, the solution is in this way. We need partial u, partial x, because u is x, y, z. So, partial u, partial x will give us y, z. We also need partial u, partial y, which is x, z. We also need partial u, partial z, which is x, y. We also deal with v. Partial v, partial x will be y plus z. I'm differentiating v with respect to x. Then partial v, partial y will be x. Partial v, partial z, partial v, partial z will be x. Partial w, partial x is 1. That is partial w, partial y equal 1. Partial w, partial z equal 1. So, we are now ready to compute the Jacobian. We know that the Jacobian of u, v, w with respect to x, y, z is defined as the third order determinant of the first derivative of each function with respect to each independent variable. So we will have partial u, partial x, partial u, partial y, partial u, partial z, partial v, partial x, partial v, partial y, partial v, partial z. We also have partial w, partial x, partial w, partial y, partial w, partial z. The determinant of this, which is the same as we fix those values, will give us x, y, then we have y plus z, then we have x, we have 1, 1, 1. Now if we do this, we can take the determinants of the third order, which we know that will be yz, then when we ignore here and here, this times here will give us x minus xz. We ignore here and here, then this time this gives us y plus z, okay, minus x plus xy. We ignore here and here, then this time this gives us y plus z minus x. You see, it is assumed that the students are familiar with determinants of third order, and because that is for the elementary part of it that we are using. It's very simple to deal with. And so we see that this will be the same as yz times 0, because x minus x is 0, minus xz times, okay, now let's multiply this at once. If you use this to times here, you will have minus xz y minus xz square, and then this time this will give us plus zx square. Then this time this gives us xy square. Then times here we have plus xyz, then minus x square y. This can go. So, and this will give us, you see, what we have here is minus x z y plus x z y. See the sign here. So those ones can go. Yeah. So that will give us minus x z square plus zx square plus x y square minus x square y. So that is the Jacobian. That is the Jacobian of u v w with respect to x, y, and z. So it's equal this. It's very simple to deal with. It's very simple. Now we want to look at the application. Properties. Sorry, look at properties of Jacobian. Then, as we continue in our studies, we'll now look at application, what we are using Jacobian for. It's very interesting if you look at them. Now, we are looking at properties of Jacobians. The number one property is that if u and v are functions of x and y respectively, then the Jacobian of u and v with respect to xy times the Jacobian of xy with respect to u and v will be equal 1. Now look at this property. If u is a function of xy, v is also a function of xy. If you take the Jacobian of u and v with respect to x times the Jacobian of x and y with respect to u and v, then the result will give you 1. And we are going to take example of this. The Jacobian that we had finished before now, where we said that x is equal r cos theta, and then y is equal r sin theta. We were asked to find the Jacobian of x, y with respect to r and theta, and also the Jacobian of r theta with respect to x and y. Yes, these are the things. So that is exactly what we said here. The Jacobian, this Jacobian that you see here, if you time this with this, it will be equal 1. That implies that from here, look at what I'm having, what I was asked. This one and this one. It means that for me to get this one, I will say Jacobian of r theta with respect to xy will be equal 1 all over the Jacobian of xy with respect to r theta, provided the Jacobian of xy all over r theta is not equal 0. Now look at that. Now you can, if you play back, you can see that when we look for Jacobian of x, y with respect to r theta, we have r. And by the time we look for the Jacobian of r and theta with respect to xy, we have 1 over r. So what it means is that if such question is asked, the simple thing that you do is to take the Jacobian of this xy with respect to theta, which you know, and then the Jacobian of this one, because the function is not expressed in terms of x and y being independent variable of r and theta. So what you do when you take the Jacobian of the function which is expressed as function of r theta, like this one here, x is a function of r and theta, y is a function of r and theta. If I am asked to take the Jacobian of r and theta with respect to x and y, you see this function is not expressed in that way. What I will do is to take the Jacobian of this one that I know, then the Jacobian of that one that is not expressed, example like this one, is 1 all over the Jacobian of the one that is expressed as the function of r and theta. And so if you play back and then use this pattern, you see how that it is very short and simple to get it. Now I'm going to take one example now to show us exactly what I'm talking about. Now let's look at this example. Given that u equal x squared minus y squared and v is equal to xy, calculate the Jacobian of xy with respect to u and v. Now, you see, this function, what we need is here, x and y are functions of u and v. But the question is not expressed in that way. The question expresses u as a function of x and y, v as a function of x and y. So what we do is to take the Jacobian of this function that is expressed, and then we know that partial u partial x is 2x, partial u partial y is minus 2y. We also know that partial v partial x is equal to y. Then partial v partial y is what? 2x. Now, by property of Jacobian, we know that the Jacobian of uv with respect to xy times the Jacobian of xy with respect to uv will be equal 1, which implies, you see what we need here. This is what the question says. So, which implies that the Jacobian of xy over uv will be equal 1 all over. We are dividing it. Look at the multiplication sign. So we are dividing it by the Jacobian of uv with respect to x and y. Okay, so that is what will give us the result of this. And then we have to take the Jacobian of uv with respect to y is the determinant, the second order determinant. Anyway, so that is 2x minus 2y, then we have 2y, then we have 2x. And that will give us, this time this will give us 4x squared. Go this we have plus 4y squared. And that is the same as writing 4x squared plus y squared. Alright. So it means that the Jacobian of x, y with respect to u and v that we need is the same as 1, because we have said it 1 all over, because 1 all over Jacobian of this. So same as 1 all over 4 x squared plus y squared. So that is the Jacobian of x, y with respect to uv. So it's very simple to deal with that properties of Jacobian. Now, we also have another property number 2. I'll see another one. if u and v are functions of x and y respectively, if u and v are functions of x and y respectively, and y are functions of r and s respectively, then the Jacobian with respect to x and y, no, with respect to s, to r and s, yes, will be equal the Jacobian of u v with respect to x y times the Jacobian of x y with respect to r and s. Now see this one. This thing that resembles chain rule, is it? But it's not chain rule anyway. But now see, if I make, you see, in this one, u v are functions of x and y, and x and y themselves, they are also functions of r and s. So, for me to take the Jacobian of u and v with respect to r and s, I have to take the Jacobian of u and v with respect to x and y times the Jacobian of x and y with respect to r and s. So, I think we need examples so that we see how it works. Let's take an example of it. Okay, so let's look at this example. If u is equal exponential x cos y, v is equal exponential x sin y, where x itself, x, is equal LR plus SM. Then y is MR minus SL. Of course, we know that L and M, they are constants. And find the Jacobian of uv with respect to rs. See that? So, in the solution, we know that from here, partial u, partial x is equal exponential x cos y. You know, as if y does not exist. So if we differentiate this, we still have exponential x, and then we keep back the cos y. We also know that partial u, partial y is partial u, partial y. Okay, as if this does not exist. To differentiate this, you have minus exponential x sin y. Alright, so we also need partial v, partial x, and that will give us exponential x cos y, then partial v, partial y, partial v, partial y, is going to give us exponential x cos y, because we are differentiating sine y, so it gives us cos y. Now we look at the Jacobian of this. We know that the Jacobian, you know, what we are looking at is Jacobian of uv with respect to xy. So Jacobian of uv with respect to x and y will be equal the second order determinant, which is exponential x cos y. Then we have minus exponential x sin y. Then we have exponential x cos y. And then we have exponential x cos y. So that when we take the determinants, we'll have, this times this will give us exponential 2x, because exponential x. To add the powers, we have cos square y. Then going like this, we have plus exponential 2x cos y sin y. When we differentiate v with respect to x, let's look at it. V with respect to x, okay, it's giving us sine. So this is sine y. So here we will have sine square y, because exponential v with respect to x is giving us sine y. The exponential v with respect to y is giving us exponential x cos y. So we have this, and this is the same thing as exponential 2x cos square y plus sine square y, which is equal exponential 2x. So it's exponential 2x because of this one, which is cos square y plus sine square y, which we know is 1. So we have exponential 2x. Now, what we need now, we want to also take the Jacobian of xy with respect to rs. That is what we want to take now. Now, Jacobian of xy all over rs will be the same as partial x, partial r, partial x, partial y. Then we have partial y, partial r, partial y, partial x. Okay, partial x. Now we know that x is equal L R plus Sn, and then y is equal M R minus Sl. So partial x, partial r is L, partial x is N, partial y, partial r is N, partial y, partial x is minus L. Therefore, the Jacobian of x, y with respect to r and s will be equal to, now it will have L, also have M, which is this, then we have M, we also have minus L. Now if we do this time this can give us minus L squared minus M squared. Look at this, because this time this minus, then when you go this way we have minus, which is the same thing as minus L squared plus M squared. You can write it that way also. Now the Jacobian of UR with UV with respect to RS is the same as the Jacobian of UV with respect to XY times the Jacobian of XY with respect to RS. So what we need now, the Jacobian of UV with respect to RS is the same as exponential 2x. We have exponential 2x there times minus, okay, times minus L squared plus m squared, which we can use this to times. We have the same thing as minus exponential 2x, then I have L squared plus m squared. So that becomes the Jacobian of uv with respect to Rs. So we are looking at this exercise. We take this as an exercise. If x is equal exponential u cos v and y is equal exponential u sin v, and find the Jacobian of x, y with respect to uv and the Jacobian of uv with respect to xy. Now remember the properties of Jacobian, so it will help you to solve this.